All right, so now we'll look at carbonic rain. So when carbon dioxide is dissolved in water, it forms carbonic acid, the same weak acid that is produced, for example, when soft drinks are carbonated. The rain dissolves some of this CO2 as it's falling from the atmosphere, and some more is really obtained in the soils from the decaying organic matter when the water flows through and percolates through the soils. So that's how the water mixes with this CO2. So carbonic acid, which is the mix of, again, CO2 and water, itself can ionize to have one very highly reactive hydrogen ion split from the bicarbonate ion. And when these ions are carried by the water to areas with rocks containing some calcite, or fully made out of calcite, which is the case in limestone and marbles, for example, the ionized carbonic acid reacts with the calcite to decompose it into calcium ion separate from the carbonic ion, as you're seeing in the chemical reaction that is written on the slide. Okay, so again, carbonic acid makes two ions, one of them, the hydrogen, being highly reactive, and then the other one, the bicarbonate ion, both of those being here. Once they react with calcite, which is one of the common minerals that many rocks are made out of, those ions from the carbonic acid react with the calcite, and they make up a salt ion of calcium and a bicarbonate ion as well. During this process, the calcium carbonate or calcite is transformed into the soluble products and carried out by the water. So this happens very, very often, especially in caverns, as you're seeing in the picture. And here, the groundwater is the carrier of the carbonic acid ions and also the carrier of the products from that reaction. So it carries them in, it reacts with the rock, and then it carries everything out. Also, many monuments and buildings are also subject to this type of weathering, particularly in urban and industrial areas where there's a lot of smog and pollution in the air, which are full of the needed compounds for said reaction to occur. Because again, they're full of CO2, and as long as water reacts with the CO2, the carbonic acid forms and is able to undergo this chemical alteration. So, to a certain degree, our influence as human has been large on chemical weathering rates. We have produced more pollutants into the atmosphere, which again can react with the rain and then act on the different materials to dissolve them, as is the case again in this acid rain. Another example of how carbonic acid, weathers some of the materials occurs for the weathering of granite. So granite is the most abundant continental rock, and it is mostly made out of feldspars and quartz, as we saw in the igneous rock chapter. Potassium feldspars or K-spars get weathered as per the reaction in the slide, as you're seeing there above. Let me point it out. Right here. So this is the K-spar, and this is the carbonic acid, and this is just some water. So when water and carbonic acid and potassium feldspars meet, a reaction occurs, and the products of it are some potassium ions, some bicarbonate ions, some silica, and another mineral. And this other mineral we call clay minerals. So through this reaction, we turn potassium feldspar into clays, which are super key for making up the inorganic component of our soils, and which are very stable under surface conditions, so they won't get weathered very easily. And then we get some potassium that will be released and available in the soils as a nutrient for plants, for example. As some of you may know, bananas have tons of potassium, which the plants originally get from that soil, and that soil gets it from the dissolution of the ions from potassium feldspar, for example. I learned that bananas actually had a lot of potassium from this kids movie, You might have seen it as well. I don't know what it's called in English, but this scientist shrinks him, his wife, and his friends. And so the kids kind of go crazy in the house, start making a party, and one of the kids is potassium deficient, and so they give him a banana and he's all better. But that's how I learned that bananas had a lot of potassium, which is really funny. Check the movie out. I think it's probably like I Shrank Ourselves or something like that. Okay, so from this byproduct, again, we get clay minerals, we get potassium, we also get some silica, as you're seeing here at the end. So the silica is also one of those byproducts of the reaction, and it forms minerals such as chert or flint, which are the same thing. And they are an amorphous cousin of quartz. So they get carried through the sediments, and then they fill in pores between grains, and also they cement them. Or they can get carried all the way to the ocean, this silica grains, where microscopic animals remove it from the water to build the hard silica shells that they are made out of. So when feldspars in this reaction gets weathered, much of what is left in the granite, which is now mostly just quartz grains, are now freed from the granite itself. So quartz, being very resistant to weathering of either kind, of either physical or chemical weathering, it tends to either get lithified into some sort of sedimentary rock, or it gets carried away to the seas where it makes these nice sandy beaches as we know them. All right, so the table above lists the weathered products of some of the most common silicate minerals that we have. Again, silicate minerals make up 92% of Earth's crust and are made up mainly of 8 elements, as I've repeated in the last few lectures. So, when these minerals are chemically weathered, they yield sodium, potassium, calcium, magnesium, ions that form soluble products, which may be removed by the groundwater. The element iron, that is one of those main 8 elements that make up silicate minerals, usually combines with oxygen, producing relatively insoluble iron oxides such as hematite and limonite. The aluminum, silica, and silicon and oxygen combine with water to produce residual clay minerals, which again are pretty stable at the surface. They're not going to get weathered away very easily. And then the remaining contents, so mostly just silicon and oxygen, tend to form the silica grain, or tend to be silica grains from the start. Quartz is then a very resistant mineral overall to weather, both due to its lack of reactability, if you would, and this is partly due to its hardness, as well as, or I guess its hardness, which will combat physical weathering very well, and its lack of chemical reactions that it can form, so that way combating chemical weathering. All right, so the chart that you see above, called Goldrick Stability Series, is used for looking at the susceptibility to weathering from the silicate minerals that we have. And somewhat unsurprisingly, if you would, it has the same order as Bowen's reaction series. So Bowen's reaction series, if you remember from chapter 4, predicted the crystallization sequence. The Goldrick Stability Series predicts how susceptible those silicate minerals will be to weathering. So in this case, olivine and calcium-rich plagioclase are going to be the most susceptible to weathering, so they're going to weather first. Olivine, having some iron, magnesium, and silicon, is going to yield mostly oxide minerals and just some freed silica. And then calcium-rich plagioclase will turn into some dissolved ions, basically, and maybe give a little bit towards clay mineral formation. And then, if you follow the order from the image in Goldrick Stability Series, you see when each mineral will weather away, or rather, how susceptible each of those silicate minerals is to weathering. So you see that quartz is the least susceptible to weathering, and that's why it's found in so many places as sediment or as sedimentary rocks. Okay, so in this slide, we are just portraying that quartz is indeed very tough to weathering, physical and chemical, more so to chemical. But it lays, quartz is going to lay at the bottom of streams. It's going to lay at sandy beaches. It's going to make up a bunch of desert dunes, and it's going to make lithified rocks. It's going to make sedimentary rocks. So in this picture right here, it's Ander in one of the many beautiful sandstones that are in the state of Utah. I have a few of my own, but I just wanted to show you Ander because I have talked about him so much, and he made your lab manual as well, so I figured I'd put him there. Okay. So again, quartz can withstand a lot of different processes, both weathering processes and erosional processes to a certain degree, and so it typically doesn't weather as easily as other minerals will. Okay, so spheroidal weathering is called in such a way because weathering starts by targeting exposed surfaces. And I mean weathering, I mean both physical and chemical, mostly chemical. These chemical weathering will, again, target the exposed surfaces and then attack any edges that the rocks may have. So it attacks the edges from 2 different sides, if you can think about it, and it attacks corners on 3 different sides, hence attacking them at a faster rate, if you would, at a growing rate. And so overall, it wears these areas down faster, and it leaves them as nice round surfaces that look like sort of spheres or sphere-like shapes, and that's why this type of features are called spheroidal weathering, because the weathering causes sphere-like shapes. The image right here shows you the progression of how that is formed, I think, pretty well. And then the image on the right shows you just another place where you can find the spheroidal weathering. Okay, so apart from the outside factors involved in chemical and mechanical weathering that split the rock into smaller pieces, and hence expose more surface area, other processes also help speed the rate at which certain rocks will weather. So these processes we'll look at in the next few slides, and they're going to be rock characteristics, climate, and also differential weathering. Okay, so from rock characteristics, here I mean all chemical traits of rocks, including mineral composition and solubility. In addition, any physical features such as joints can be very important to note because water tends to penetrate these cracks and these features. So as an example to this type of process, I guess, that allows for weathering, let's take this granite and marble headstones shown in the slide above. Both of these headstones are in the same cemetery, so we should expect them to have been exposed nearly to the same atmospheric agents. The marble headstone that you see on the right, made out of calcite from 1874, is hard to read as it has been heavily chemically weathered. Calcite, as I told you, dissolves readily even into weak acidic solutions, right? It dissolves due to the carbonic rain, or acid rain, I should say. Carbonic acid rain. In contrast, the granite that is the picture on the left, which is made mostly out of non-ferromagnesian silicate minerals, most of which lie lower in Bowen's reaction series, and which, according to Goldrick's stability series, are least susceptible to weathering. Again, the granite has handled the chemical weathering quite well, despite its contact with the same acidic solution that the marble had been in contact with. Again, this headstone was probably made in 1968 or 1969 at the latest, so a few years older than the marble one, and you can see all the writings perfectly because it hasn't weathered nearly as fast as the marble headstone.